Okay. So, let's continue with the new topic, that is a classification tree, and that is a predictive model. Okay. So here's what we did in the previous class. I gave you a bunch of papers, right? 12 of them actually, and each piece of paper had this stick figure, right? So kind of let me give you a background again. So this is a pretend bank. Okay, I had 12 customers in the past, so this is my historical data. Okay, so each customer, what's the difference between customers? Each customer has a specific shape of head, that can be either square or circle, shape of the body, and that can be either rectangle or oval, and the body color. It can be either white or gray. And also what I know about each customer is if they defaulted on the loan before, such as mortgage, right? So these yeses and nos, they're all recorded on the top of each one of my customers, okay? So here's what we did. Basically, the idea behind classification tree is this. I'm starting off with my data set, full data set, as a mixture of responses yes and no, zeros and ones. I don't remember if we discussed that, probably we did, right? But how typically, numerically, is no encoded as a number? No is 0 and yes is 1. Same thing true and false, right? False is 0, true is 1. That's normally how yes, no, true, false are encoded in the data. Okay, so and the mixture right now for me, I believe we did this, right? So here is the result of our previous class exercise. Okay, so right now I'm starting with all of my data set being a mixed bag of responses, yes and no, almost 50-50, right? Not quite, but almost. 7 out of 12 yeses and 5 out of 12 no's. So what I want to do is build a model that will allow me to predict for each customer whether or not they're yes or no. Okay? So for that, what I want to do is start splitting them by the variables, by the predictor variables. So I'm splitting my data set by predictor variables. So these three things that are different about each customer, head shape, body shape, and body color, are the variables, predictors. Okay? So I'm trying to predict right now, based on the head shape, body shape, and the body color, who will default on the loan, yes, and who will not default on the loan, no. So therefore my target, really, so let me go ahead and write it over here, okay? Target variable is, well, let me quote unquote, default. Default question mark. The possible answers are yes, defaulted, no, did not default, okay? So these variables become my predictors, okay? Predictors. So I'm trying to predict the target based on the set of predictors. That's what I'm doing, okay? And the way how classification tree does that is we're trying to split the data set based on any of my predictor variables. So the first thing that I did is I said, okay, let's split the data set based on the head shape, right? So 12 customers, 3 of them have circular heads, right? As you can see right here, and 9 of them have square heads, right? So if I do the split, if I separate my initial 12-person data set into 3 and 9 with circular heads and square heads, then within each set, what I'm looking for is as pure separation, yeses and nos, as possible. So ideally, again, what I want to see is all yeses and 0 nos. Like for example, 3 out of 3 are yeses and 0 out of 3 are nos. That would be ideal, okay? Or ideal separation, again, everything yeses versus 0 nos, or no yeses versus everything no's, right? So here, if I had 0 out of 9 yeses and 9 out of 9 no, that would be ideal case, right? That would be a pure data set. So I'm calling data set pure if it contains not a mixture of responses, but responses of one type, preferably. All yeses, no no's, or all no's, no yeses. That is a pure data set. I achieved clean separation of my target values, right? yes versus no. Okay. So the worst case scenario is when I have 50-50. Okay. Half responses are yes, another half of responses are no. Okay. That would be almost like, okay, flipping a coin, really, right? Half customers are yes, half of no's. I don't know how to classify them. Flip a coin at each customer, right? That would be a random decision pretty much, okay? So we separated that based on the shape of the head, right? Squares versus circles, and what we found is this. Square heads, they're not separating cleanly, right? So out of 9 square heads, it's almost 50-50 mixture again, right? 5 out of 9 yeses and 4 out of 9 no's. Very close to half and half, right? That's not what I'm looking for. So this is kind of a bad set. Over here in the circular heads, right, I have slightly better division, right? I have 2/3 versus 1/3, so 66 versus 33%, but still not ideal, right? So here's what I want you to do, you guys, okay? Go ahead and put the mixture back together again, right? All 12 people. And now, do 2 things, okay? Thing number 1, try to separate them based on the, what's the other one? Body shape, right? Ovals versus rectangles, and see what kind of percentages, yes versus no, you will have at each subset, rectangles and ovals, okay? And write that down. Then put it back together and try to separate based on the body color. White bodies versus gray bodies, and see what kind of mixture you're going to get. And then when you're done, let's kind of spend about 5 minutes doing this, okay? When you're done, tell me what, in your opinion, is the best split to separate as cleanly yeses from no's. Is it based on the head shape, body shape, or body color? Joel, do you have a question? Do you have a question?
No, you already answered.
Okay, good. So go ahead and start splitting things, right, based on body shape and body color. And then in a few minutes, tell me what do you think is the best thing to do. Split the 12 people based on the head shape, body shape, or body color, okay? So I'm going to keep quiet for a little bit, and you work. Just to clarify, each time when you separate them, it's by one characteristic only, okay? So do 2 characteristics. All right, so how many of you are done? Pretty much. All right. Tell me what you found to be the best predictor to split. Body shape? Everybody? Okay. I think you're right. So let's take a look. I'm going to do the bad one first, okay? The body color. That's not a good predictor, okay? So, again, I'm going to do the same thing as I did in the previous class, right? So if I have my all observations in one data set, as I originally do, right? Then yeses and nos, I forgot what they were, 7 out of 12 and 5 out of 12, okay. So 7 is first, right? Yeah, 7 is first. Okay, so 7 out of 12 and 5 out of 12. Almost 50-50, which sucks, right? So therefore, I'm going to split based on the body color. So therefore, white bodies are going to be on the right side, gray are going to be on the left and gray on the right. Okay, so here's what happens, right? So, okay, I'm going to just drag them. Okay, so gray are right here, and everybody else has white body, right? So I'm going to select them all and just move. It's not a good thing, right? So let's do it in groups. So here is group 1, and I have another group right here, and then everybody else. Come on. Everybody else, I'm just going to move right here, okay? So let's take a look at what ratios do I have. I'm looking at the ratios really, right? What is the percentage of yeses versus percentage of nos in each resulting subgroups, right? So I split my data set into subsets, right? So over here, yes, what's the ratio? 1 out of 2. And therefore no is also 1 out of 2. Is that a good split? It's as bad as it can be, right? Half and half. Doesn't really give me any information, right? Half people in this set defaulted, half people didn't default. It's a coin flip, right? Not a good thing. So over here, among customers with white bodies, right, I have again yeses and nos. So what do I know about them? I know that there are 10 of them, right? And how many yeses do I have? 1, 2, 3, 4, 5, 6, right? 6 yeses out of 10, and therefore 4 nos out of 10. Also almost 50-50, right? For that to be 50-50, it has to be 5 and 5. But it's 6 and 4, right? But it's close, okay? Almost a coin flip, right? So if I'm splitting based on the body color, that does not get me any closer to actually understanding who will default and who will not default. In each subgroup, it's still almost 50-50 chance, right? Not a good thing. So now I'm going to do the last one, okay? That you guys told me that it's the best, and I trust you because you're smart. All right, so again, I'm going to start with all observations in one set, right? All. Among all, my percentages are 7 out of 12 and 5 out of 12. Now I'm separating based on body shape, right? Body shape. Okay. So over here on the left, I'm going to have, I don't know, rectangles. And on the right, I'm going to have ovals. Okay. So let me start with ovals first. So these two guys, okay, they go over here, and this one, also their neighbor, and this one, also their neighbor, and the last one is right here, bam. Okay, oh, and another one, right? Did you see that one? Okay, and then these guys move. Why is it only one? And that one, I'm going to move him right. Whoa! How do I undo? Now it is very small. Oh, yeah. That's a big customer. Alright, so this guy moves over here, and I have two more. There you go. It's a little clumsy, but we managed, right? Okay, so let's take a look at this is a good split. So now in each subgroups, how many observations do I have? 6, right? So among oval bodies, yes and no. How many yeses do I have? 2 yeses and 4 no's, right? So 2 out of 6 are yeses and 4 out of 6 are no's. Okay, fine. I mean, that's not the best thing, right? But it's better than everything that I had so far. Well, in one case I had also 2/3 versus 1/3, right? It's kind of the same thing, right? 2/3 and 1/3. But among rectangles, what do I have? Yeses and no's. I have 1, 2, 3, 4, 5. 5 yeses, right? 5 out of 6. And no's is only 1 out of 6. That's the best split that I've seen so far, right? So therefore, you're right, okay? I achieved almost clean separation of yeses from no's in the rectangle body customers, right? Now this one is still a mixed bag, right? But among the 3 splits, I tried to split on the head shape, body color, and now body shape. It seems that the body shape is the best first split, right? It gives me best separation of yeses versus no's, right? In at least one of the subsets, okay? And that's basically the idea behind classification tree, okay? So what's going to happen next is this. I took 3 predictors. I had 3 predictors to begin with, right? Body shape, body color, and head shape, and I tried to split my data set based on each one of them, right? And then I saw that the best split is going to be the body shape, okay? So that's going to be my first step. So the best first predictor, the most predictive, how should I say, the predictor with the highest predictive power, therefore, is the body shape, okay? Because I split on that first. It gives me the cleanest separation. The resulting 2 subsets are the cleanest of all 3 possibilities, right? But now here's what I can do. I can go ahead and start all over again and now treat my resulting 2 subsets as starting point. So I can do the same thing again, right? So out of 3 variables, right? Where's my, yeah. So out of 3 predictors, I already used the body shape, agree? Done, okay? I choose that as my first predictor to split, okay? I still have head shape and I still have body color. I can keep splitting based on these 2 predictors. So let's take a look. And again, the idea basically for me is to separate yeses from no's. Let's take a look at rectangles, for example, right? In rectangular bodies, right, I have 5 yeses out of 6 and 1 no out of 6. And I'm splitting, my 2 possible splits can be either head shape or body shape. How can I separate yeses from no's? Can you tell me? Head shape, right? Because one customer with circular head was a no, right? Everybody else was a yes, and they all have square heads, right? So therefore, my second split over here will be on head shape, okay? Head shape. All right, so I have ovals over here. No, I have circles, right? Circle and square. So if I do that, then, well, circle is going to be only one customer, right? Really, okay? And that customer is a no, right? So I can formulate, I mean, let me go ahead and drag it over here, right? So I'm going to go ahead and say that in this subset, yeses are 0 out of 1 and no's are 1 out of 1. This is a clean subset, right? It contains only one response, only no, and 0 yeses, right? That's as clean as it gets. This is my ideal case, right? Now, the other one is even better, right? If I go ahead and take these guys, as I just did actually, right, and put them in their own group right here. Well, this one, substandard, this is a tall guy right here, right? Alright. So now I have again yes and no, and they're all yeses, right? So 5 out of 5 are yeses and 0 out of 5 are no's. This is again a clean subset, not a mixture, right? All yeses, 0 no's. Okay, cool. Now let's take a look at ovals. What do we do with ovals? Head shape again, right? So I can go ahead and separate circles, right? Circle again versus square. And what I'm going to get is squares are these 4 guys, so they go right here. And circles, I don't have much space actually for them. So I'm going to put them right here. Okay. Yeah, it's kind of messy, but you get the idea, right? So my 2 subsets. For circles, yes is, that's everybody, right? I have 2 circle heads, this one and this one. And therefore 2 out of 2 are defaulted. Agree? And 0 out of 2. Again, this is a clean set, not a mixture of yes, no. Okay? Same thing in my square heads, right? Yes versus no. Nobody out of 4 defaulted, and everybody out of 4 did not default, right? So actually, what I ended up with are all clean nodes. Okay? Now this is pretty much the only time when you will see something like that in this class. Okay? Typically, in the final nodes, you have a mixture of yes and no responses. Okay? As you will see in just 1 second when we're going to start looking at Titanic example. Okay? But this is the idea behind the classification tree. Okay? So let me summarize that. First of all, is it a supervised or an unsupervised method? Supervised. Why? Because I have a target variable, right? Because my target, let's go back to the very beginning, right? My target variable is yes, no, did they default, okay? I have 1 column in my data which I'm targeting specifically, right? I'm trying to predict who will default on the loan and who will not default on the loan. I have a target. Therefore, by definition, it's a supervised learning, okay? So, second question is, there are 2 types of supervised predictor models, okay? There are classification models and there are regression models. Which one is that, do you think? Classification. Again, how do you know? Because if your target is categorical, then this is what? Classification, right? If your target is numerical, this is a regression, okay? Ours is not a numerical target. Yes, no. I mean, we can formally assign 0 for the no, 1 for yes, but we can just easily assign 10 and 20, minus 15 and minus 64, right? It's our choice, really. It's kind of label that we give, not a real number, okay? So our target, yes, no, is categorical. Hence, we're dealing with classification, okay, model. So therefore, classification tree is a supervised method because there is a target, and it's a classification model because the target is categorical. Okay. Now, also you can see, where is my last thing right here, right? Also, you can see this one, yeah, body shape, right? As you can see, what I did basically is I took the initial data set, then I separated based on 1 predictor, which is body shape, right? I got 2 resulting subsets, right? Then I said, let's pretend as if we're starting over. Let's just treat each one of these subsets as a new starting set. And let's see if we can split it further to achieve better separation of yes versus no. And indeed, we were able to, right? We split here on head shape. By the way, I don't know if you realized it or not, but we could split on the body color, and it would be just the same result. Right? I probably should have pointed out that back then, right? So this set we split on one of the remaining variables, and it was possible to achieve an even better split, right? And the other data set we did the same thing, right? We treated that as our starting point, as if we're kind of starting from ground zero. This is our set, and we split it by the remaining predictor, one of the predictors, right? So that we separate yeses from nos as cleanly as possible. how far it can go. How far can I keep splitting? Not just in this example, but in general. It can keep going, right? So, for example, let's say if I had here, I mean, it's not a realistic example, right? Body shape, you know, body color. That's not how banks decide on the mortgage, right? What do banks use as predictors? What do you think? Credit score, salary, level of education, right? How many kids do you have? What's your level of education? Whole bunch of things, right? So that's not how they do it, but it kind of gives you an idea, okay? So, and I can actually keep going further and further if it gives me a better split between yes and no root, okay? So this procedure can continue, right? So if I had bigger set or more variables, this one, for example, could split, I mean, potentially even further based on something else, based on some other variables. But in this case, I didn't need to split this one because it's already pure, right? I already achieved separation of yeses and nos. Why should I split any further? I already can tell 100% yeses from 0% nos or other way around, right? So basically, this procedure called CART stands for classification and regression tree. Classification and regression tree. That's ugly. Okay, regression tree. Okay. So what CART does basically keeps splitting your resulting subsets further and further and further until one of the two things happen. Okay, or three things. Right. Number one, you already achieved the split, which is perfect. No need to split any further. Right. Just like in our case. Number two, you run out of variables to split. That's it. There is nothing else. Okay, and these are really two scenarios. Okay, so you keep splitting each subset into more subsets, deeper and deeper and deeper. They become smaller and smaller and smaller, right? And you run out of variables to split. There are no more variables, and you still have kind of a dirty subset, which is a mixture of yeses and nos. CART will say, okay, this is as far as I can go because nothing else is left. I split on everything that's available to me. That's it. We're stopping here, okay? All right. So therefore, it's called recursive partitioning. Recursive because what I do here is I split first set based on some variable, then resulting sets I treat as new sets and split them, and then smaller sets I treat as new sets and keep splitting them, right? So it goes as deep. I mean, it can get very deep. The tree can grow pretty quickly, okay, and it can become a big tree, okay. So that's the recursion part, okay? To split the set, each set we treat as a new, split it further, and it keeps going on, okay? And partitioning is when you separate things based on some parameter, some criteria, right? Okay. Now, another thing that I wanted to point out is some terminology, okay? This is my initial set with everything, right? My entire data set, okay? This is called root. So if you can imagine, this is a tree, this is an upside down tree, right? Because it grows from the root, and then you keep adding branches, right? It goes down, right? Not up, just like regular tree does. So it's kind of an upside down tree. So therefore, our top node with all the data is called root node, okay? Now, these nodes are not final, right? Because I keep splitting. I still split them, right? So these roots are not final. They're called internal roots, okay? So, or decision nodes. Not root nodes, okay? Decision nodes. And this is where the tree stops, right? Because first of all, because I achieved perfect split already, right? They're all 100 versus 0 or 0 versus 100, right? All of them, right? So therefore, there is no further split. These guys right here at the bottom of my tree are called terminal nodes. And that's what I'm looking for really in each tree. Terminal node, okay? Terminal node. So decision nodes is just a way to get to the terminal node, okay? I'm sure it sounds a little confusing, but you will see what I mean in just 1 second. We want to get classification tree done using R/R Studio. We can totally do it, okay? I'll go ahead and check right now, actually. Go on your C drive, look in C drive folder data, and there you should see the file that we used about a week ago, Titanic. We're going to do useless exercise, practically useless exercise, but very useful educationally speaking. Do you still have Titanic data set on your C drives in the folder data? You do? Wonderful. Okay, let's turn our attention to RStudio. Go ahead and launch RStudio. By now, all of you should have the icon for RStudio permanently anchored in your start taskbar, right? So go ahead and launch RStudio. Should I make it bigger? Okay. Magical magnifier. We call upon thee. All right. 200%. That should be enough. Okay. So go ahead and create a new script, my dear friends. You remember how to create new script? There is a plus sign, right? And you just pick new R script. Then, what's the very first thing that we always do before we start plugging away analyzing data? Comment, Smallman. Comment if you want comment. Yeah. What's the very first thing that you need to do? Now, read the data from the file, right? You remember how to read the data? Read.csv, right? And I'm reading that into the variable. So, okay, since you don't remember much, let's start as if you don't remember much. Okay, so read data from what type of file? CSV file. From Titanic.csv, okay? So I'm going to call this Titanic data, Titanic underscore data. And here's how we read it, right? I'm going to say variable Titanic underscore data will contain the result of the function. And as I start typing read, it says read.csv. Fine. This is the one that I need, right? Remember we did something like that before? When we looked at the data summary and we looked at the, what did we do? Tabular summary, proportions, we calculated proportions, and then we did the bar chart, and then two-dimensional crosstab. You probably remember that. And what do I need to tell to the function? Where to find the file. And this should be fully specified path, right? So it's not enough for me to say, hey, somewhere on my computer there is a file, Titanic.csv, please find it for me. No, this is computer, okay? You need to be precise. So therefore, I'm going to say it's on the drive C, in the folder data, and it's called Titanic.csv, right? So when I run this line, and you remember how to run the line, right? You can either click on the run button right here, or you can do what? Control Enter, same thing, right? So, oopsie. You see that? I misspelled it, right? Titanic.csv, Titanic.csv. You have to be precise, right? Okay, cool. So now that the data is in, here's what I'm going to do. I'm not going to do the file structure. Well, actually, let's do file structure, okay? Let's pretend nothing happened before, okay? So now I want to look at structure of the file, of the data, okay? Let me do this. Let's look at structure of the data. It's typically a good idea. So how do we look at the structure of the data? STR. Can you guess what STR stands for? Structure. And my data is called Titanic underscore data, right? That's the name of my internal variable which holds all the data from the file Titanic.csv, okay? So when I run it, when I run this line, it will tell me, yes, dear sir, here's your structure. You have 2201 lines, basically passengers, observations, and they are distributed among class, so that they traveled on Titanic, first crew, etc., right? Age, We don't have a number, we have just a label for them, child versus adult. And we have sex, male, female, self-explanatory. And this one, survived, yes or no. Okay, cool. Well, ladies and gentlemen, here's what I'm going to try and predict. Well, let me ask you this, okay? What do you think I should try and predict in this file? What would you do? I give you the file with 5 columns, right? No, 4 columns, right? Age, no, class, age, sex, and survive. Which one do you think we should try and predict based on the rest of them? Survive, right? Who will likely survive on Titanic based on what their gender was, age, child, adult, and which class they traveled, right? So therefore, I'm going to build a classification tree. Here comes again the demonstration of the power of R. R natively cannot do the classification trees. Okay? So I cannot just type away, let's predict something. Okay, let's build a classification tree. Okay? I need to call an external library that can do the classification tree model for me. Okay? That means that I need to install it first. Okay? So, and there are 2 ways, right? So let's actually install the library by typing things. So I'm going to comment things, okay? Because I feel like I need to. Okay, so install. The library that does the classification is called rpart. R stands for recursive, part stands for partitioning, right? It keeps splitting the set until there is no more good split, or you run out of things to split on, okay? So install package rpart, recursive partitioning, okay? Here's how the package is installed. We did that before, you probably forgot, okay? I'm just guessing. Gmodels, we installed the package Gmodels to do the cross-tab, right, about a week ago. So this time around I'm going to say install .packages, and the package name is same thing, no spaces, rpart, okay? Go ahead and type install .packages, the name of the package rpart, okay? And then run the line. It will probably tell you some nasty messages, some warnings, right? But at the end, it will say package successfully unpacked. Do you have that? Success, right? Red warnings basically mean that it's either installed already, or it will tell you that, hey, it's built under older version of R, so it may not work nicely for you. Just ignore that, okay? So as long as it says successfully unpacked, we're good to go, okay? Now I installed it on my machine. Now I need to load it into the memory, right? How do I do that? I have to call library, right? So now I have to load the package rpart, recursive partitioning into working memory, into my RAM. Okay, so I'm going to say library. That's how I load any library which is installed, right? And I'm just loading library rpart, this one. Okay. Now it'll give you, like, it gave me nasty red warning. It's not deadly, right? We discussed it. Typically red color is not good, but this time around it's okay, right? Because it says warning, your package was built under version 3.6.1, which probably means that this is a more newer version, so swim at your own risk, so to speak, right? Okay, I'm fine with that. So now I have rpart loaded. Well, ladies and gentlemen, here comes the weird part, okay? And this is probably what you should put on your cheat sheet should we have a test coming next week. Wink. Okay? I don't require you to memorize this, okay? Although it would be nice. But here's how I built the model. So now I'm ready to actually ask the software to do the same splitting as what we did manually, right? Okay, so first of all, everything, that's my personal preference, everything that I do, I like to have stored somewhere, okay, in some object or variable. So I'm going to be very descriptive, okay, so comment here, build a classification tree model, okay. All right, so, and I'm going to call my model, I'm going to give it a huge long name, very descriptive, okay, Titanic _ classification _ tree underscore model. How do you like them apples? That's a really long name. Now note that I don't have any spaces. Can you guess why? We discussed it, right? Because computers don't like spaces. If you have a space, that means there is part 1 and part 2. It will treat them differently. And that's not what I want, right? So if you have a compelling need to separate words, do it with underscore, okay? This is so-called snake notations, right? Replacing spaces with underscores. Okay, so inside this variable, here's the weird part, okay? Inside this variable, I'm going to record the result of the function R part. Stands for what? R stands for recursive, part stands for partitioning. Excellent. Okay, I have to tell this function 3 things. Thing number 1, what is my target and what are my predictors? Okay, here's how it's done. We have to be also mindful of the uppercase versus lowercase. Remember we discussed that R is case sensitive, right? If I look at my data structure, what do I see? I have 3 variables, all of them start with uppercase, right? So my target, we discussed it. What's my target? Survive, capital S. So I'm typing survive, okay? And I put tilde. Tilde means this is my target, and what comes after tilde is a bunch of my predictors. And predictors, I'm going to use all of them, okay? So I'm going to use age, capital A. If you do lowercase, it will not understand you, okay? And I'm going to say plus. Next one is sex, capital S, plus. The last one, what was the last one? Class, capital C, right? Class. Now, and then I put comma after that. Warning, plus is not an addition. It doesn't tell, you don't tell the program to add age and sex and class together. Plus means you're predicting, so literally how to read this line is we're predicting the variable survive based on age and sex and class. Okay? You're not adding anything. It's just a way to tell the software that this is the set of your predictors. Class doesn't mean add, okay? It means and this and this and this, okay? Next thing that I have to tell, which data to use. So I'm going to say data, and look at that. As I start typing, it says, yeah, I know what you mean. There is such thing as data equals. Okay, data equals. How is my data called? Tell me. Titanic underscore data, right? Use this one. So Titanic, oopsie, Titanic underscore data, comma, and the last one, cart. This is method cart, right? Cart stands for classification and regression tree, okay? It can do both of them. We will discuss regression trees next week. So this is a classification tree, right? Because my target is what? Categorical, okay? So I can be building classification tree or I can be building regression tree. This time I want classification tree. So I'm going to say method that you have to use is quote unquote class. And the class stands for classification. Okay? And that's it. That's basically how we write this command. Okay? So I'm asking R to build for me a model to classify customers as survivors and non-survivors based on age, sex, and class using classification tree and the data that I just read from the file. Go ahead and run this line. Method tells you if this is a classification or regression. So today we're discussing classification. Therefore, method equals class. That's it. Okay. Next week I'll show you what regression does. Okay. And the very last thing that I want to do is this. Okay. I understand that we're running out of time, right? We have about 3 minutes. I run this line. It's blue, right? That means success, but I don't see anything, right? Show me the tree. Okay, that would be nice. So here is how I can show the trees. Okay, so for that I need another library. So let me put a comment: install and load library It's called rpart.plot. Self-explanatory what it does, right? It takes the classification tree, the result of the recursive partitioning, and plots it for you, okay? So, same thing, I'm going to install .packages, and the package is called rpart.plot. Okay, run this line. And after I install the package, what's the next step? Load it into the memory. I installed it on the machine. Now I have to bring it into the RAM, right? Read and write memory, right? Random access. It's called random access memory. Library. Oops. Library. Okay, I'm loading library rpart.plot. And when you do that, it will probably tell you same warning, right? I don't know if it will or not. For me, it does the warning. It says, yeah, it was built under older versions, so it may or may not swim at your own risk. Fine with that, okay? And the last thing that I'm going to do today is show the classification tree. So this is the cool part, okay? So now, display classification tree model, okay? All I'm doing really is I'm saying rpart.plot and then the name of my model. What's the name of my model? How did I call my model? Exactly. This ugly long name is my model, right? So I'm gonna say Titanic, and as I start typing, it shows me, yeah, I know a little, like few things that start with Titanic. Yeah, that's the one. Run this thing, and there you go. This is my classification tree. How do you like them apples? Did you get the classification tree to show? No? Who didn't? Failed at some point in time. Okay. Well, you know what to do, right? First of all, there is this video, which I am going to upload. Second, I'm going to post that script online as well, so download the script. But what I would do is, I would do it myself, okay? So, all the steps, so view the video, okay? And all the steps that we did, do them again on your machine and make sure that the tree shows up, okay? And next class, we're going to discuss two things. Thing number one, how to interpret this thing. You can see that at the bottom, how do I call these nodes at the bottom? Terminal nodes, right? They are the most important ones for the interpretation of the result. We're going to look at them. Okay, what do these yeses and no's mean? Okay, and number two, on Friday, if we have enough time, I hope we will, we're going to discuss how do we look at the accuracy of the tree, because tree is not 100% accurate. Okay, there are errors in the classification. How do we calculate accuracy of the tree? Okay. So we're done for today. I'm going to post the file and the video.
Could you scroll up?
Yeah.